The Physics of Waves, Day 2, or Day 91 in the notes. In yesterday's notes, Day 90, the main idea is what is a wave, what is the main characteristic of a wave. It's common to all waves, and that is that waves are vibrations or disturbances or wiggles or jiggles that transmit energy without transmitting a physical material. The energy goes from point A to point B. There is no material or mass that goes from point A to point B. All right, today we have the velocity of a wave, calculating the velocity of a wave. And the equation is V, the velocity, equals the wavelength times the frequency. We will be using this quite a bit this quarter, this semester. The velocity, or the wavelength, is lambda, measured in units of meters, standard. Frequency is F. We want to use hertz for frequency, and then velocity is V, and we want to use the units of meters per second, standard units. For example, if you play the musical note C, sometimes it's called middle C, it has a frequency of 256 hertz and a wavelength of 1.34 meters at room temperature, and we'll talk about the differences that occur at different temperatures in a subsequent lecture. But we simply plug in here V equals lambda, wavelength, times frequency. So the velocity of this sound wave created by this musical note, whether it's played on any instrument, piano, guitar, saxophone, is the wavelength, which is 1.34 meters. That's good as far as units, and 256 hertz. Simply multiply there, and you get a velocity of 343 meters per second. That's over 700 miles per hour. I'll do the conversion on that in a few minutes here. But what about if you play the musical A, which is above, the next one above C, higher frequency, higher pitch, because the frequency is correlated to the pitch of a sound wave, and we'll talk about that once again in a future lecture. But just to show the calculation one more time, V, velocity, equals wavelength times frequency. The wavelength, now you got to watch out here, we don't want centimeters, we want meters. That's 0.78 meters times the given frequency here, which is okay, 440 hertz. So if we take those two numbers, multiply them together, lo and behold, we end up with 343 meters per second, which is the same as we got in part 1 here. Now, so it turns out that all sound waves, all notes, all pitches of sound travel at the same speed, which is a good thing because, for example, if you're in a concert hall listening to an orchestra play a whole bunch of different notes at the same time, it's a good thing they all travel at the same speed and get to your ears at the same time so they all sound good together the way they were intended. All right, so all sound waves travel at 343 meters per second at room temperature, a comfortable temperature, 70 degrees Fahrenheit. If you do the conversion here, that's 769 miles per hour. That's sometimes called, well, the speed of sound, or Mach 1. Mach 2 would be twice that speed. We'll talk more about that later. Now, electromagnetic waves travel at a different speed, almost 1,000,000 times faster, and that is 3.00 times 10 to the 8th meters per second. That's over or around 700 million miles per hour. We won't need to use that number. But electromagnetic waves travel that speed in a vacuum, regardless of the temperature. They're not temperature dependent like sound is. Sound will travel at slightly different speeds at different temperatures. Once again, we'll talk about that later. But for now, the speed of sound is 343 meters per second. The speed of electromagnetic waves is 3 times 10 to the 8th meters per second. Now, electromagnetic waves include all of the following listed here. Circle those in blue. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, and there's some others, but these are the main ones that we'll be studying. All of these are electromagnetic, and they all travel at this very, very high speed. Sometimes this is called the speed limit for the universe. Nothing can travel faster than that. It's called the speed of light. And we typically will give this a symbol. We'll call that c. In other words, c, little c, like an E equals mc squared, is 3.00 times 10 to the 8th meters per second. It's the speed of light, but it's the speed of all electromagnetic waves. For example, here, number 3. Radio waves given off by radio stations. Take, for example, WGN radio, which has a frequency of 720 kilohertz. The velocity of those waves is indeed 3.00 times 10 to the 8th meters per second, because radio waves are an electromagnetic wave. So if we plug into V equals lambda f, wavelength times frequency, here we're looking for the wavelength of these waves. So we plug in 3 times 10 to the 8th, 3.00 times 10 to the 8th, shortcut, 3 times 10 to the 8th, equals the wavelength times 720 times 10 to the 3rd meters per second, hertz, or you could say 720,000. But if you do the math here, that wavelength of those radio waves, 417 meters. And I happen to know that those radio waves are probably in the room you're sitting in right now, if you're in Chicago, Illinois, or near Chicago, Illinois. Those waves are coming through your room, coming through the walls in your room, and you could prove this by taking your radio out, putting it on a table, tuning into station or frequency 720 kilohertz, and you would receive those radio waves in that radio, and that radio would convert them to sound waves that would then travel from the radio speaker to your ears at a speed of 343 meters per second if you're at room temperature. Green light. You can have all different colors of light, but green light in particular, once again, we're going to do the calculation. V equals lambda f. Green light is an electromagnetic wave. It has a speed of 3 times 10 to the 8th meters per second, equals the wavelength. Now here the wavelength is 532 nanometers. N is nano. And nano is 10 to the negative 9th meters. We have to remember that here. Or you could have to look that up or ask the teacher. So 532 times 10 to the negative 9th meters times the frequency here. We're going to calculate the frequency first, because keep in mind we need to get the period here, but it's according to this equation we can get the frequency first. We can do this in steps. 5.6 times 10 to the 14th hertz. That's the frequency of green light vibrations as it travels through a room, vacuum, and air is close to a vacuum as far as visible light is concerned. If it's not a vacuum, the light actually gets slowed down a little bit by air, but not by much, not by any substantial amount. So we're still considering the speed to be 3 times 10 to the 8th meters per second. But the period now, as we learned yesterday, is 1 over the frequency. So the period is 1 over 5.6 times 10 to the 14th hertz. So there's 2 equations we've used so far in this unit. V equals lambda f, the velocity of a wave, and then T equals 1 over f, or f equals 1 over T, which is just a variation of this equation. If you do the computation here, you get T equals 1.8 times 10 to the negative 15th seconds. Let me circle that in blue. 1.8 times 10 to the negative 15th seconds. That's the period of vibration. That's how long it takes to make one vibration of green light, which is a part of any kind of white light you might have in your room, or any specific green light you also might have. It has that period. Wave interference. You have constructive and destructive interference. And basically the names pretty much tell you what's going on here. Interference of waves is when you superimpose 2 waves, put 2 waves together. In the left-hand diagram here, we have constructive interference. You have 2 waves, the blue wave and the red wave, which we say are in phase. In other words, their peaks, their crests, match each other. Their troughs match each other. So if you place them on top of each other, they would be additive and they would make a stronger wave. The resultant wave basically would be the summation of the heights of the two waves that were already given. So the purple wave there is the resulting wave from adding those two or having those two waves interfere with each other, and we have constructive interference. If you had, for example, two sound waves that were constructively interfering with each other, you would get a very, very loud sound. If you had two light waves that were interfering with each other, you'd get a very, very bright light. If you had two water waves that were interfering with each other constructively, in all these cases, you'd get a very, very tall water wave. It always makes for a bigger effect, larger amplitude wave. As opposed to, excuse me, destructive interference, if you have the peaks matching the troughs matching the peaks, and you combine those two waves, they basically cancel each other out, and you get nothing, you get a flat line. Once again, if you had sound waves that were exhibiting destructive interference, it'd be like the two waves would be added together, and they would cancel out, and you get quietness. That's how noise-canceling headphones work. They essentially produce a sound wave that's opposite the one it's detecting, and it cancels out that background noise. With light waves, if you had two light waves that had destructive interference, you'd get darkness. And water waves that destructively interfere with each other, you'd get a flat surface. Finally here, a standing wave, which is a pattern, because of interference, it's a fixed pattern of nodes and antinodes. When a wave is reflected back onto itself. And I will show you this demonstration in the hallway, but let me give you some definitions here. A node is a location of no displacement or no vibration, and an antinode is a location of maximum displacement. All musical instruments generate some sort of standing wave. And I'll show you an example for a stringed instrument. That's a little bit easier to show. I'll show you in class and on the next slide or the next lecture here. This is supposed to be a depiction, a model of what happens to a stringed instrument when you pluck the string or hit the string with a hammer like in a piano. The string vibrates. It's fixed or tied down at two ends, and it vibrates. And it's some kind of combination of this, and you'll see an example in class. But some terminology here. In the first case, the top one is called the fundamental, or the first harmonic. The second one is called the first overtone, or the second harmonic. So it goes first harmonic, second harmonic, third harmonic, fourth harmonic, but depending on how you want to talk about this, and it can be a little confusing, the fourth harmonic, for example, is the third overtone. What this is supposed to be like, and if you take the top one, the fundamental, the red is supposed to be the string vibrating back and forth from the red position to the blue position, from the red position, it vibrates back and forth. Same thing in the second harmonic. It's not two different strings, it's the same string vibrating back and forth. Now in each case we have nodes and antinodes. Let's take the fourth one, the third harmonic. I'm sorry, the fourth harmonic, it's the third overtone. This fourth case here has five nodes. So there are nodes here. There's five of them. 1, 2, 3, 4, 5. Those are spots where the string, or the string, that part of the string is not moving. Because the string is moving from red position to blue position, and you have wide spots that are antinodes, 4 of them in this case. Let's see if I can squeeze this in here. Antinodes. There are 4 antinodes. There's this spot, this spot, this spot, and this spot. Let me see if I can make them a little bigger, point them out. Those theoretical blue dots there's no blue dots, but they're vibrating from those positions back to the bottom positions, back and forth, back and forth, back and forth. So let's another example. The first overtone, the second harmonic. I'll circle it in blue. All right. It has 3 nodes. I'll highlight those in black. 1, 2, 3 nodes, 2 antinodes where there's big, wide, fat spots, so to speak. Lastly here, if we call the length of the string L, where it's tied down on both ends, that's the length. L stands for length. what happens here is the length of the string, if we ignore any stretching of the string, is set. It's tied between those two ends. The length from one end to the other end is L. Forget about the curved part, but it's a length of L, straight line distance. In the first case, L equals 1/2 of a wave. 1/2 the wavelength. I'm going to call that wavelength number 1. In the second case, L is not changing here, is a full wave, or 2/2. Each little spot or segment between two nodes is a half a wave. And what you have here, and I'll highlight it, is a wave that repeats itself. It goes up and then down and then up. Well, it would repeat itself. It would go up and then down again, but that's one cycle. That's one wavelength. And mathematically here, that would be like 2/2 for lambda 2. And you'll see a pattern here, I hope. L equals, for the third harmonic, second overtone, is 3/2 of a wave, or waves. There are 3 segments there. So that's 3/2, or 1.5 waves, or 1.5 lambda 3. And then L, which is not changing for the fourth case here, the fourth harmonic, is 4/2. So the fourth wavelength is, the fourth length is 2 times, in other words, 4 divided by 2 is 2 times the wavelength. As you can see here, the wavelength is getting smaller and smaller and smaller. So for example, if L was 100 meters, now let's say 60 meters, 60 centimeters, L equals 60 centimeters. In the first case, all right, if L is 60 centimeters, if you plug in L in for the first harmonic, plug in 60 for L in all 4 of these cases, and I'll kind of do the math in my head, or you can do it off on a calculator. But in this first case here, lambda 1, if you plugged in 60 for L, you multiply both sides by 2, you get 120 centimeters for the first wavelength. In the second case, 2/2 is 1, so that 2/2 would basically cancel out. And L is wavelength 2. In other words, wavelength 2 was equal to L, so lambda 2 will be 60 centimeters. It's a smaller wavelength, half the wavelength. Lambda 3, right, if you plug in 60 for L and do the algebra, so because L is not changing, you're going to multiply by 2, which is 120, but divide by 3, you get 40 centimeters. The wavelength is getting smaller and smaller. Number 4, lambda 4, if L is 60, once again, do the math here, you get lambda 4 equals 30 centimeters. So the wavelength is getting smaller and smaller as the harmonics go up and up and up. And you can keep going with the same pattern.